Hi, in this video I will show you how you can build your own computer with simple logic gates and flip-flops. I made a video explaining logic gates and flip-flops, so if you are not familiar with those devices, click on the video description to watch that video first. Every computer has some inputs, some outputs, and some processing unit that turns those inputs to your desired outputs. I will show you what that processing step is. But first, I should point out that the clock input is absolutely necessary and fundamental to the system. No computer can exist without a clock input. All modern computers process information in a series of states. A state is a moment of time where the processor knows some information and knows where to go next based on those information. These states make the processing actually happen. Your laptop or PC can have millions or billions of states. But here, let's start with a simple example of a system with only 3 states. I represent them with these 3 circles. This is called a state diagram. I number these states 0, 1, and 2. But let's turn these numbers to binary. I explain later why naming states in binary is so convenient. If you don't know how to turn numbers into their binary representation, you can use Google to find them. Also, it doesn't matter how many zeros is on the left side of the number. Let's also say that if the system is in state 0, it moves to a state 1, and then moves to a state 2, and finally returns to state 0 to create a loop. Now you have to decide what you want your system do in those states. Let's say we want our system to say hi. We first build a 7-segment display like this, made out of LED strips. Now when it says H, these LEDs should light up. And when it says I, these 2 LEDs should light up. We can name the LED segments from A to G. You can see that for H, B, C, E, F, and G LEDs should light up. And for I, just E and F. Back to our state diagram, we want the system to show letter H as state 1 and letter I as state 2 and nothing as state 0. From this diagram we can build a table. This is called a truth table. We just want to put everything from the diagram into this table. We start from the current state 0, 0. We see that the diagram goes from state 0, 0 to 0, 1. So under the next state column in front of the 0, 0, we write 0, 1. The diagram also shows that in state 0, 1, outputs B, C, E, F, and G are on. So we put 1 under those outputs. Similarly, we see that after 0, 1, the system goes to state 1, 0. And outputs E and F are on. Finally, the system goes from state 1, 0 back to state 0, 0, and all of the outputs are off. You can see here that outputs A and D will never turn on, so I can leave them out. Now, this is why writing the number of states in binary is so important. We have to assign a flip-flop, D flip-flop in this case, to each digit of number of states. Here we have 3 states and we use 2 digits. So I call the first D flip-flop D1 and the second D2. Then I write D1 plus to represent the next state of D1 and D2 plus to represent the next state of D2. Now that our truth table is complete, we can move on to Karnaugh maps or K-maps in short. K-maps help us to calculate logic equations for our circuit. Here we have only 2 variables, D1 and D2, so we use a 2-variable map. The map is like a 2 by 2 square, with each square assign a number to it. Remember how did we assign D1 and D2? D1 was the left hand side digit and D2 was the right hand side digit. Now if you look closely at this map, you see that on this row D1 is always on. So we call this row D1, and on this row D1 is always off, so we call it not D1. Similarly, on this column D2 is on, and on this column D2 is off. so we call them D2 and not D2 respectively. Now we look at our truth table and start calculating our next states of flip-flop and outputs. First, for D1 plus. For the state 0, 0, D1 plus is 0, so we put 0 in the square 0, 0. For the state 0, 1, D1 plus is 1, so we put 1 in the square 0, 1. For the state 1, 0, D1 plus is also 0, so we put 0 at the square 1, 0. Now for the square 1, 1, we don't have a corresponding state for 1, 1, so we just put an X in the square 1, 1. This is called a don't care sign. Now there is 4 general rules for K-mapping. 1. You have to group all the ones. 2. Groups must be continuous. 3. Groups can include up, down, left and right squares. And 4. Don't cares can be grouped with other ones, but you don't necessarily have to group them. And remember, it's always better to have the bigger and fewer groups to simplify your logic equations. Here we have only a 1 and a don't care, so we can group them together. Now this group includes 2 rows of D1 and not D1 and 1 column of D2. But because D1 and not D1 are opposite of each other, they cancel each other out, so we don't consider them. The only thing that is left is D2, so we write D1 plus is equal to D2. This is our first equation. If we do the same process for D2 plus, we reach at this map. Now we can't group this one diagonally with this don't care, so we have to group the one by itself. The group includes not D1 and not D2, and we write D2 plus equals not D1 and not D2. But as you can see, the outputs B, C and G are also exactly like D2 plus, so we can add those to the same equation. For E and F, we have this map, and we can group these two ones. Remember, we don't have to group the don't care. We can see that D2 and not D2 cancels and we only left with the not D1. An equation would be E equals F equals not D1. Now that we have our logic equations, we can move on and draw our circuit diagram and physically make it. But that's for the next video. See you soon and thank you for watching.